This presentation is on our transport phenomena exam question and solution. So let's begin. So our group somehow wanted to use rockets in order to develop a question for an exam of a course like this. And we thought it was a great idea because rockets use large-scale combustion to provide the thrust that they need to get into space. That combustion creates a lot of heat, very high temperature in excess of 3000 kelvins. And they also actually use the liquid fuel to cool the engine walls at the same time, which is a little bit of an interesting setup compared to your typical combustion engines. So we developed a question that is based on basically the way that a rocket works, and this is going to test a fourth year student's knowledge on both transport phenomena and also some past basic heat transfer principles that they may have learned in other courses. So the research article that we'll be basing our question off of was actually titled Numerical Simulation of Liquid Rocket Engine Thrust Chamber Regenerative Cooling. Now, what that basically means is that they were trying to figure out the actual amount of heat that's being transferred through the wall from the side where the exhaust is, the hot side, to the coolant side, which is where your liquid fuel is. And the original research paper used CFD simulations in order to determine all the data that they needed. But we thought that this would be a great inspiration for a question if we could just modify it so that it was more easily solvable just by simplification for students in a fourth year course.
In our question, the student will be tasked with verifying the design choices by conducting a heat Shell balance on the intermediate wall and a velocity Shell balance on the coolant layer, while also utilizing various concepts of heat transfer such as conduction and convection. This combination of concepts is done to encourage an individual to recognize the interdisciplinary nature of transport phenomena.
So this is our project question. During combustion in large thrust rockets, the exhaust gas can reach temperatures in excess of 3000 Kelvin. It is imperative that the chamber walls are constantly cooled to prevent the temperature from reaching the melting point of the chamber walls material. As such, Figure 1, which will be shown in the next couple of slides, shows an internal view of a model combustion chamber. This chamber has 5 evenly distributed spacers of 0.5 millimeter thickness that form channels running up the length that collectively use a continuous flow of liquid ethanol at 0.1 kilograms per second to provide the much needed cooling to the metal chamber inner wall. The question is then divided into sub-questions, which are questions A to F, that the student must solve. But from this paragraph alone, it is evident that the question will involve energy and momentum transfer. So the information that the student will be given is that they have a coolant mass flow rate of 0.1 kilograms per second and a thickness of 0.5 millimeters for each of the 5 evenly distributed spacers. The properties for both aluminum and ethanol with their respective temperatures will also be given. So Figure 1 and Figure 2 are the diagrams that will be given to the student. In Figure 1, we have an expanded view of the rocket engine. However, we will focus more on the combustion chamber, which is the cylindrical section. And in Figure 2, we have the annular cross-section of the combustion chamber with the given radii.
To start us off, the student is made to determine the inner wall coolant layer temperature. This is done through an energy Shell balance. The student has been provided with a heat flux through the chamber wall of 1.375 megawatts per meter squared, which is generated by the combustion. Some of the assumptions that the student will have to use throughout our question are steady state, laminar flow, incompressible fluid, and constant material properties. The analysis of this Shell balance starts with writing down the energy equation and simplifying it. To do this, the student must understand that the heat flux is constant in the z direction and that there is no heat generated within the system. Doing so will net them the equation dRQR over dr is equal to 0, which they will then integrate to get RQR is equal to C1, or simply QR, the heat flux, is equal to C1 over R. Once they have this, the student must realize that the boundary being investigated is at the wall, and as such, C1 over R cannot be simplified to 0. But instead, C1 is to be solved for using our first boundary condition, which is at R equals 30 millimeters, QR is equal to 1.375 megawatts per meter squared. Doing so will net them C1 is equal to 41,250 watts per meter. Moving on, they will now use Fourier's law of conduction to form another equation, which is negative K dt over dr is equal to 41,250 over r. Once they have this, they can integrate it and apply their second boundary condition, which is at r equals to 30 millimeters, T is equal to 540 Kelvin. Once they have this, they can solve for C2, which is equal to negative 310 Kelvin. Subbing everything back in will allow them to solve for their coolant layer inner wall temperature, which is 517.73 Kelvin.
For part B, the student is asked to find the heat transfer rate through the coolant. This knowledge has to come from past thermodynamics courses to know that the heat transfer rate is equal to the area times the heat transfer coefficient times the change in temperature, which the student has all that information, so this just is more about remembering from past courses. So for part C, they have to determine the overall temperature increase in the coolant. Again, this is from past thermodynamics courses where the change in temperature is equal to that heat transfer rate divided by the mass flow rate times the specific heat capacity of the fluid, which is all given. And finally for part D, will the system fail? This is kind of a concept question to understand that you don't want your coolant to boil and you're given the temperature that it will boil at, so you're just comparing the total temperature change to the coolant's boiling point, and we see that it ends up becoming less. So no, the system will not fail. So part E asks for a velocity profile equation for the coolant layers. So this will start with your basic shell balance diagram and then performing a momentum balance on that shell, which will ultimately lead to the equation seen at the bottom here. And the next step for the student is to know what can be canceled out of this based on some initial assumptions, such as the fact that the velocity in the z direction is only dependent on r. The velocity in the r direction is going to end up being 0. And the pressure is also dependent on z as well. So once they clean up and follow the usual steps and then apply their assumptions, they're going to end up having a nice little equation after the assumptions. Here it is. And then they can also just neaten this up just a little bit, just so that way the integrals later on becomes easier to solve. So one thing they'll notice after they integrate that initial equation is that they'll have a constant which they have no way of determining at this time. So what they'll have to intuitively know is that at some point in the flow field there'll be a surface, hypothetical surface, which will have a maximum velocity will be 0. So using that knowledge, they'll be able to set up the equation properly, perform further integrations, resub values in to solve for the constants, all pretty standard. And then ultimately they will end up with their final velocity distribution, which looks a little bit complicated, which will lead us into part F, which is plotting this. So now that we have our equation, the student's going to be asked to draw a diagram of the coolant fluid velocity profile. The picture that we're displaying here was one out of the textbook, which has shear stress or the momentum flux distribution, which is not required for the student. They only have to draw the velocity distribution. But other than that, it just needs to be a well-labeled diagram, and as long as they have the equation correct, they can sub in whatever values they like and they'll get a nice, easy-to-draw diagram.
In conclusion, our question was designed to test the cumulative knowledge of a fourth-year engineering student. This was done through utilizing key concepts from transport phenomena such as energy and momentum shell balances. We also included concepts from previous years such as heat transfer. Our end goal was to demonstrate the interdisciplinary nature of engineering through this combination. Thank you for listening.